Okay, let's get back to shortest paths with the negative length. So we recall that we saw Dijkstra's algorithm for finding shortest paths from a single source when all the edge lengths are non-negative, right? So Dijkstra's algorithm can be thought of as BFS, but with weights, right? An efficient implementation of BFS on the implicit graph that is obtained by splitting an edge, or you can think of it directly. And now we want to think about a graph having edge lengths which can be negative, right? And if that happens, then the Dijkstra's algorithm can fail. We saw an example of that. And the reason Dijkstra's algorithm fails, just to recap, is the fact that Dijkstra's algorithm is designed under the principle that the shortest path distances along a shortest path increase, right? That happens only if the edge lengths are non-negative. But if they can be negative, the edge I can have a shortest path, and the distance can be in the middle can be above the distance at the end. So we cannot explore the vertices in increasing order of shortest path distance. Okay, so that's why it fails. Okay, so there's another issue that comes up in shortest paths with negative lengths. There could be negative length cycles in a graph, right? You know, if you look at this graph, you know, and ask what is the shortest path from S to T, it is not obvious, right? What it should be, because if you look at this cycle here in red, you see that the length of the cycle is negative, minus 16 plus 11 plus 3, which is minus 2. So in principle, you could go around the cycle many times and go to T. So the distance keeps decreasing, right? So now we need to think, what should our problem be, right? So you can ask for a shortest simple path. That's a valid question. Or you can ask for a shortest walk. Both are valid questions, right? When you have negative lengths or non-negative lengths. If you have all the lengths are non-negative, then asking for the shortest walk length is the same as asking for a shortest path length, right? That makes sense? Yeah, because if you, why would you go around visiting a vertex more than once if all the lengths are non-negative? It doesn't change the length, right? You would find the shortest walk is the same as the shortest path. While if there are negative length cycles, then the shortest walk could be minus infinity, right? Because I can go around the same negative length cycle again and again. While the shortest path is well defined, right? Because the path can have at most n edges, right? But it turns out that finding the shortest path when there are negative length edges is NP hard. So we don't know how to solve it efficiently, right? So you may want to solve it, but we don't know how to solve it. Okay? So instead, we will settle for finding the shortest walk length, right? So we want to find the shortest walk length, right? So more precisely, again, just to make sure that we are on the same page, a path doesn't allow you to repeat vertices, while a walk allows you to repeat vertices, right? So we are now only interested in shortest walk lengths, right? Not shortest path. We allow walks. Now then, you know, what is the shortest walk length between S and T? Well, there are two cases. If there's a negative length cycle that I can go and visit many times and go to T, then clearly the shortest walk length is minus infinity, right? Okay. If there is no negative length cycle, then the shortest walk length is finite and it is well defined, right? Because if I take any walk and if there is no, why would I have a cycle if it is not, length is not negative, right? I can take it out and I'll get a shorter walk. So either the shortest walk from S to T is minus infinity, that happens when there is a negative length cycle, or it is finite and well defined, right? It's the same. So we will be in that situation. We want to do the following. I give you a graph which has edge lengths can be negative or non-negative, and S and T, and our algorithmic goal is either say that because there is a negative length cycle that S can reach and go to T, the distance is minus infinity, right? Or, oh look, there is no negative length cycle, so I will give you the right distance. Is that okay? So those are the problems we're going to tackle. Yeah? Okay. How do we do this, right? Okay. So an important caveat here is that once you have this negative length edges, the undirected graph case cannot be reduced to the directed graph case, like we could if the lengths were non-negative. If all the lengths are non-negative, we can reduce the undirected shortest path problem to a directed shortest path problem by taking an edge and splitting it into two not splitting it, changing it into two directed edges. But if the lengths can be negative, what will happen? If you have an undirected graph and negative length edges, what happens? Yeah, you create a negative length cycle. If you take a negative length edge and make it into two directed edges going this way and this way with the same negative length, then I already created a negative length cycle, right? Even though the undirected graph may not have a negative length cycle to begin with. Okay? So you cannot do the reduction. Okay? So we will only confine ourselves to the shortest path problem with negative length edges when the graph is directed, because we cannot reduce the undirected graph to the directed graph. We can actually solve the undirected graph problem as well, except that it requires completely different techniques. Okay? You need much more advanced techniques for undirected graphs for this problem than for directed graphs, which is kind of surprising because typically it's the other way around, right? But it's a caveat. You cannot reduce the undirected graph case to the directed graph case in this particular problem. Okay. So why negative lengths? Do we care? Right? Are there any applications, right? None of you asked this question, but a natural question is, most shortest path problem seems to be, why would you care about negative lengths, right? That's a valid question. There are many reasons, and due to lack of time, I will let you look at the slides, right? One is, one simple application that comes up is in currency trading. Okay, suppose I want to many of you are aware of maybe arbitrage opportunities in currency trading. For example, the exchange rate is how do we trade in the, right? It's a long story, but suppose I identify that I can make money by saying, oh, I can convert dollars to euros and euros to some other currency, Indian rupees, and then come back to dollars. Can I make money like that? Why would I be? Does it make sense to be able to do that? Right? It depends on the exchange rate, no? So, suppose if I can make money by converting dollars to euros, euros to rupees, and come back to dollars, I would, right? Why would I not, right? The question is, who is controlling this, right? Okay, it depends on the exchange rate, right? If I told you the exchange rate, you can check whether I can make money like this or not, right? Okay, but so that's the question, right? If I tell you the exchange rates between every currency, and I ask you, can you make the money by making this cycle, right, of arbitrage? That question can be reduced to finding whether the graph has a negative length cycle. Okay, easily. It's not hard at all. Okay, so now, so that's an interesting application, right? And people do this. They actually are looking, the big financial trading companies, that's what they do, right? They try to make money by doing arbitrage like that, but the market corrects itself, right? If there's an arbitrage opportunity, you'd start trading, the market adjusts itself, right? So that's why they buy faster and faster computers to do it better than the other person, right? The reason why they spend a lot of money on computers and algorithms people is to take advantage of the microseconds that are available when there is a gap between the adjustment of the rates and the ability to make money when they execute trades, right? That's a whole field in itself, but that this is one place where it comes up, and there are many other reasons. So I won't bore you with the applications right now because of lack of time. So okay, we have an algorithmic problem. It's kind of interesting. Whether you care about applications or not, it seems, well, if you can solve it, why not, right? It's a clean, simple problem, and that we should have these good problems that we can use for other reductions and so on. Okay, so clearly the Dijkstra's algorithm doesn't work, right? The idea behind Dijkstra's algorithm doesn't work. It's not just the algorithm doesn't work, so we have to think fresh, right? How do we design an algorithm when this kind of feature is there? So let's go back to what helped us design a shortest path algorithm, right? So the following principle, first assume there's no negative length cycle for simplicity. So let's look at shortest path from S to some vertex V0 to Vk. Even when there are negative length edges, it still remains the case that if this is the shortest path from V0 to Vk, then a prefix of a path is a shortest path from V0 to Vi. The only question is, we cannot say that the distance to Vi is less than the distance to Vk, right? All right? Okay, so that's the only difference, okay? Now, so this means that we cannot explore the graph in increasing order of distance from the source if the lengths are negative, but what is still true is that if I want to go from S to Vk and it's the shortest path, then the guy who is on my path has a shortest path with fewer number of edges, no? Yeah? I mean, if this is the shortest path, the guy in the middle has the shortest path which has fewer number of edges. Yeah? I mean, otherwise how will I get to that guy, right? Okay, so now we can take advantage of that property rather than distance property, okay? So what is that basic property? And we will try to do this using dynamic programming, in fact, okay? And so for that, here is a definition, right? This is a clever algorithm, so let me tell, right? First, assume that every vertex can be reached by the source, right? Otherwise, you can throw them out. They are not interesting, right? Is that okay? That's a simple assumption which you can do, right? If some vertex is not reachable from the source, throw it out. Yeah. So everybody is reachable from the source. For now, assume also there is no shortest path cycle, but though that's a negative length cycle, but that's not relevant. Too important. Okay. So I'm going to define a quantity dvk. What is dvk? It's the shortest walk distance from S to V using at most k edges in the walk. Is the definition clear? dvk is among all walks from S to V using at most k edges in the walk. What is the shortest walk length? Is that definition clear? Yeah? Simple definition, right? Okay. What is distance, real distance from S to V if there is no negative length cycle? I claim it is ds n minus 1. If there is no negative length cycle, I have a shortest path, right? Yeah? How many edges can it have? It cannot have more than n minus 1 edges, right? Yeah? Agreed? Okay, so I want to find dv n minus 1 for everybody, right? Because that's the shortest path length, right? Okay? Okay, now the question is, can we write a recursion for dvk in terms of k? Right? If we can do that, then we can find them recursively, right? Okay, so I claim it's very simple actually, right? What is dvk? dvk is the shortest walk length from S to V using at most k edges, right? What is it? It's either dvk minus 1. What does that mean? That the shortest walk from S to V doesn't need k edges. It is less, uses only k minus 1 edges or less. Then it is dvk minus 1. Or if really I need to use k, I want to find the shortest walk with at most k edges, then how does that walk look like? It starts at S, goes to V and has k edges, right? Let's look at the guy before me on that walk of length k. Who is that guy? Some guy U, right? Okay, I claim that the walk from S to U, now how many edges does it have? K minus 1, right? That better be the shortest walk from S to U using at most K minus 1 edges, right? Is it okay? If not, I will find some other walk from S to U with at most K minus 1 edges and then go from U to V. That will only make my walk shorter, no? Okay? So my claim is, what is dvk? It's the min of dvk minus 1, and look at all the vertices that can reach V in one step, right? It's an edge. It is min over all U belongs to the vertices duk minus 1 plus the length of the edge from U to V. Is this recurrence okay? Yeah? Any questions on the recurrence? Yeah? So I'm asking, okay, let's take the case, what is the base case? Well, ds0 is 0, right? Because, I don't need to use any edges to go from S to itself. ds0 is 0. dv0 is what? Infinity, right? There is no way to go from any vertex other than the source using 0 edges, right? So by definition, we'll call it infinity. Okay? Right? Okay. So let me run an example. It's much easier to understand it using an example. Okay. So let's see what the recursion is doing, right? So okay, what are we trying to compute, right? Oh. Okay, I don't understand what this pen is doing. Okay. B, C, yeah, that is S. It is acting funny. Okay. E, F, E, F. Okay. All right. You have to bear with me. I don't know what the. Okay. So what is a k equal to 0 is, what is the distance from S to each of the vertices with using 0 edges? That's a base case, right? For S it is what? 0. For A it is infinity, 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 infinity. Okay. What about k equal to 1? What are we trying to find? We are finding the shortest walk from S to that vertex using at most one edge, right? Okay. So what is ds k equal to 1? It is, okay, again we think of it, right? How can I get to S with one edge? Well, I can't unless I have a self loop, which I don't, right? So it is either ds k minus 1, ds 0, right? Or from some vertex I have an edge to S, right? But that is infinity for everybody else because dv0 is infinity. So basically I just get 0 for this guy, right? But let's look at for A. What is dA1? That is the shortest walk from S to A using one edge, right? What is it? Well, we know from this graph, you can see that it is either the min of dA0, right? Because I don't need to use 1, right? Or it is what? Look at all the edges coming into A, okay? I could come into A from any of those vertices, right? Okay, what are all the vertices coming, edges coming into A? D and S, right? Okay, so it is D. You look at how many, what is the shortest walk from S to that vertex using 0 edges, and then the length of that edge, right? Okay, does it make sense? So for A, everybody else is other than S is infinity, so it is just 6, right? Okay, for B it is what? B it is 4, C it is 3, and the rest stay infinity. Yeah, agreed? Yeah, so this is still an easy case, so let's do the next case, which is more interesting. Yeah. I did, right, because it is 0, ds0 plus 6 is what I get, right? Because the walk from S to A with one edge, okay, I look back and say, if it has a walk is of length 1 edge, the previous guy must have a walk of length 0, no? And from that I take the edge length, that will give me the shortest walk of length 1, right? So for A, the length of walk 0 from S to itself is 0 plus 6, that I get 6. For everybody else it is infinity plus whatever it is, so it is infinity. Yeah, that's how we think, right? Okay, now 2 is more interesting, right? So what is the shortest walk length from S to some vertex with 2 edges, right? For S to S it is 0. For S to A, what should it be? It is either 6 or, again you do the calculation, how can you come into A? Well, this is still infinity, right? For K minus 1, I mean it's 1, so you just get 6. What about B though? See, B, dB2 is what? Either it's min of dB1, what if your dB1 is 4, right? Or you can also get to B in which way? You can get to from C, right? Right? So it is, if I want to get from S to B using at most 2 edges, I can go from S to C using at most 1 edge, that is 3, and then I can take this edge, so I get 2, right? So it is 2, yeah? So C is, okay, what about C? Well, it doesn't change, so you get 3 for D. Let's see for D. For D, what is it now? For D, this is, if I want to come here, it is infinity, from here it is infinity, but from here I already have dB1 is 4, so it will be 4. Yeah? Is it okay? Yeah? So be careful, right? It is not 3 plus 0, it is 4 plus 0, right? Because I'm constraining you to use only 2 edges, no? Yeah? Is the recursion clear? Yeah? Yeah? What is dB2? I mean, sorry, the distance to D using at most 2 edges, right? It's either the distance using at most 1 edge, which we already know, which is infinity, or min of that, or I look at all the incoming edges, right? If I want to have a walk of length 2 from S to D using 2 edges, well, I look at how I can get there using 2 edges, look at the previous guy that I could come from, that walk must have at most 1 edge, right? Okay, so I could get to D by going through B, and then I have the walk, if I want 2 edges to D, then I can only use 1 edge to get to B, and that length is 4. Right? So it is 4 plus this length of this edge, 0, right? I do have to do the min over all possibilities of getting to D, and that's what I get. Yeah? Is it clear what we're doing? Yeah? Okay, questions? Okay, so then we can compute all of this, right? I don't know what it is for E. F is also, F will be 9 and E will be what? Still infinity, right? Okay. Okay, do you get the idea? Do we need to do one more, or you're happy? Okay, good. Okay, you see the recursion, right? Okay, okay. So if you do this computation, I can keep doing it, right? As the walk length increases. Okay. Okay, so this is the Bellman-Ford algorithm. What do? You find shortest walks with increasing number of hops, right? Edges. Okay, so it's a very simple. You are memorizing this recursion, right? dvk, and so for k equal to n minus 1, you keep doing it, right? And you get the, for k equal to 1 to n minus 1, for each vertex, you just use the recursion. dvk is, you start out with dvk minus 1, and you see if you can improve, right? For each edge that comes into that vertex, you check it is dvk is the min of dvk, the existing value of dvk, and duk minus 1 plus the length of the edge. What we did, right? Okay. So what is the running time of this algorithm? Sorry? That's not clear, right? We'll come to that. Okay. If there is no negative length cycle, then the shortest path can have at most n minus 1 edges, right? Okay, then we'll be happy. This will be fine if there is no negative length cycle, right? At the end of the algorithm, dv n minus 1 would give me the shortest path with at most n minus 1 edges, and that will be the right shortest path distance if there is no negative length cycle. No negative length cycle. There can be cycles, that's fine. If the length of the cycle is every cycle is positive, then I actually don't need to use cycles. Paths are sufficient, right? Shortest walks would be the same as shortest paths. Okay. Okay, what is the running time of this algorithm? A lot. Okay, that's not the answer, right? We're looking for. We need numbers, right? In terms of n and m, how long will this algorithm take? Sorry? N squared m. Why n squared m? Let's look. Well, there are n outer loops, yeah. But what about the inner loop? How long will the inner loop take? For each vertex, okay, if you're crude, you can say it's n again, and inside is m again, so it's a weak upper bound, right? But let's look at what we are doing for each vertex here. We are only looking at its incoming arcs, right? Yeah, we are not spending m time per vertex, we are only looking at its incoming arcs. So the total work in the entire for loop is the number of edges of the graph. Yeah, right? Because we're only looking at the incoming arcs for each vertex, and that's total, right? We look at arc only once, right? So n outer loops, and the total work inside the loop is m, right? So nm, right? Yeah, you don't agree? Why? Okay, how much work are we doing per vertex here? It depends on my in degree, right? Okay, I look at an edge only once in this entire. Why? Let me see. If I have an adjacency list, I look at an edge only once, no? No. In one inside loop, how many times will I look at an edge? Only once, right? Right? Yeah. M plus n. I see. It's always m plus n, but if the graph is connected, right, then m is always n, so it's not a big deal. Yeah. Yeah. It's true m plus n. N plus m, okay, fine, right. All right, so the total work, running time is mn, or okay, and how much space do we use? Sorry? How much space are we using? You've already forgotten dp, right? Mn, why? What is the size of the table we are creating? What does the table look like? N vertices, n minus k is going from 1 to n minus 1, right? 0 to n minus 1. It's n squared, right? Sorry? That we haven't optimized yet, right? I'm just, if I did the entire thing, I'm going to do n square, right? Yeah. Okay. Yeah. So the space is m plus n square, right? We have to store the graphs. Yeah. Okay. Okay. All right. Okay. That's the Bellman-Ford algorithm. Now we have to say something more, right? Well, as we said, do we need to, if you only want to calculate the final row or the final column, each column depends only on the previous guy, right? Yeah. To calculate dvk, we only look at dvk minus 1, right, of all the vertices. So if you did the space saving trick, we will only need n space extra, right? Yeah. Okay. So you can do that. You don't even have to keep track of this, but don't worry about that. You can easily save space. So space can be reduced to m plus n. Okay, now what guarantee, see, the part of the problem I have is to actually check whether there is a negative length cycle, right? This algorithm will give me the right distances if I promise you that there is no negative length cycle. Yeah? But part of my job is to figure out whether there is a negative length cycle or not. So you can't, that's not a nice thing, right? So question is, can we adapt the algorithm to find a negative length cycle if there is one? A negative length cycle. Yeah, of course, we should do that. Otherwise, it's not a very useful algorithm, right? Yeah, that's good. That's the right idea. So what, let's think intuitively. What should happen if there is a negative length cycle? Okay. If there's a negative length cycle, it means that if I keep increasing k, I should get lower and lower values of the distance, right? Because remember, I'm finding shortest walks, right? Not shortest paths, right? So if there is a negative length cycle, if I keep increasing the length of the walk, I should get lower and lower values, right? So I should be able to detect by changing k, trying more values of k, and if I keep getting distances are going down, I should realize that, there must be a negative length cycle. Yeah? Intuitively, does it make sense? Because if there is a negative length cycle, the walk length should go down to minus infinity eventually, right? That means it keeps going down and down and down as I increase k, because then I can go around the cycle many times. Okay? Okay. So in fact, that's true. And so what you do in the algorithm is you go to n minus 1, and then you do one more. You find dv n as well. If you have, and we'll prove this or at least sketch it, that for any vertex, if dv n is less than dv n minus 1, that means the walk length decreased when I made the walk length n from n minus 1, then I can detect that it has a negative length cycle. Okay? All right? Okay, so what is the algorithm? I compute dv0, dv1, dv2, dv3, dvn minus 1, dvn. Okay? If there is no negative length cycle, we know that dvn minus 1 should not be more than dvn, right? Because if there is no negative length cycle, I need at most n minus 1 edges in my path. But if I find a vertex which has dvn less than dvn minus 1, then I'm guaranteed that there is a negative length cycle. Okay? Right? That's the algorithm finally. Okay? So the algorithm is, first do this n minus 1 iterations, and do one more iterations at the end, and in the last iteration, if you actually find a vertex has reduced its distance, then there is a negative length cycle. Okay? Now it's a little bit, it is not completely obvious that you just need to do one more iteration. Okay? It is sort of intuitive that if you do many more iterations, you will eventually detect that there is a negative length cycle. But the fact that you will detect it right away after one more iteration is a little less obvious. Okay? Is that clear? It's not completely obvious, right? If I say one more iteration is sufficient, why is it? Yeah, you have to think a little bit more about the proof. Okay? All right? But that's the algorithm, right? Simple enough? Yeah, that's the Bellman-Ford algorithm. Okay? Okay. So what is the correctness? Well, by induction, dvk is, if you believe the recursion, we are computing dvk correctly, right? That's correct. Okay? So if there is no negative length cycle, then we don't need more than n minus 1 edges in any walk, and we'll figure it out, right? The answer is correct if there is no negative length cycle. Now, now we want to worry about the negative length cycle, right? So this is a lemma. G has a negative length cycle reachable from S if and only if there is some node V such that dVn is less than dVn minus 1. Okay. 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 So basically, let me give you an intuition. The full formal proof is a little tricky, right? So what happens? Why will the distance change if the negative length cycle is there, right? Okay. Suppose G has a negative length cycle. Okay. I want to convince you that some vertex distance will go down in the nth iteration. Suppose G has a negative length cycle, right? I want to claim that when we do the last iteration, somebody's distance will actually go down. Yeah, some vertex distance will go down, right? Okay, so look at the lemma statement. If G has a negative length cycle reachable from S, then there is some node V in the cycle such that dVn is less than dVn minus 1. Yeah, is the statement clear? That means doing the last iteration we can detect that there is a negative length cycle. Okay? Okay. So how do we do this? Let's prove by contradiction. Suppose there is a negative length cycle. How does it look like? Okay, I don't know. What does it mean that the length of the cycle is negative length? That the edge lengths are sum is, right? Okay, so first observation is that because everybody is reachable from S, after n minus 1 iterations, everybody will have a finite value on them. Okay, because that's easy to see that after n minus 1 iterations, everybody will have a finite. I cannot have infinity on anybody. Because at the end of, after n minus 1 iterations, because everybody is reachable from S, they will have some finite value. Okay, that's just a technicality. So what happens in the last iteration? Okay, we'll prove by contradiction. C is a negative length cycle. That means the sum of the edge lengths is let's number these vertices: V3, V4, V5, V6. Oh God! All right. Okay. So suppose dVn for everybody did not change. That means it stayed the same in the nth iteration. What does that mean? If dVn was not less than dVn minus 1, what does it mean? So this guy is V1, this guy, so let's say that, this is completely ridiculous. Okay, so this is V1, V2, V3, V4, V5, V6. Okay. Okay. If let's look at this edge, right? dV. All right, sorry. Yeah. Yeah. So what I'm trying to prove is that if there is a negative length cycle, then somebody's distance in the last iteration has to go down. Okay. I'm saying, I'm going to assume there's a negative length cycle and that nobody's distance in the last iteration changed. Okay. Then I'll get a contradiction. Okay. If I get a contradiction, I'm happy, right? That means, right? That's what I'm means. Yeah. Okay. Okay. I'll hand wave because of this pen issue, right? So if these guys distance did not change in the last iteration, why is that the case? Then it means that the distance after n minus 1 iterations, the dV3 n minus 1 plus the length of this edge must be greater than or equal to d4 n minus 1. Right? If dV3 n minus 1 is less than dV4 n minus 1 plus this length of this, I would update this guy, right? So let's look at the distance at the end of the n minus 1 iteration. Okay. If I did not change anybody's distance in the nth iteration, what can I claim for this edge? I can claim that d4n, right, d4n minus 1 is less than equal to dv3n minus 1 plus the length of this edge. Okay, I get that it's inequality, right? If it was not, I would change it in the next iteration. So I get that inequality for all of them, and if I add all of them, everything will cancel, and I will get the property that the length of the cycle is actually not positive. But I assume that the length of the cycle is negative. So that's the contradiction. Okay? So if the length of the cycle is negative, then one guy has to go down in the next iteration. In every iteration, if one guy has to go down. Okay? So that's the proof that you need to think about a little bit. Okay? So if there is a negative length cycle, somebody has to go down, right? All right? If the current distances in one guy has to go down. If everybody is going to stay put, that means the length of the cycle must be positive. All right? It's a small, it's good to think about it offline. Okay? Yeah? All right. So, okay. So that's the correctness of the negative cycle detection, right? So what happens here is that, so we saw that if S can reach a negative length cycle, the algorithm will detect it, right? But maybe there is a negative length cycle and S cannot reach it. How can we detect whether a graph has a negative length cycle in the whole graph? One obvious thing is, for every vertex, check this algorithm, right? But that take a long time, right? For every vertex you run Bellman-Ford, already it is taking n times m, right? So we want to change that and make it a little bit more efficient. And here is a small trick just to, so if you want to make sure that to check whether a graph has a negative length cycle, you should create a new source such that it is reachable, it reaches everybody. Okay? So I mean, this is a small technicality. So what I'm trying to say is the following. Suppose the graph is like this, right? Here is S. Here is a negative length cycle, -1, -1, -1. And S cannot reach this cycle because there's no edge from S to this, right? So if you did Bellman-Ford from S, it won't detect that there is a negative length cycle in the graph because nothing is reachable from S, right? So it'll just say everybody is infinity, it'll all stay infinity, right? Because now nobody is reachable from S. So which vertex should you do a Bellman-Ford from to detect a negative length cycle, right? It is hard to know, right? So instead of doing that way, what you do is that you take this graph and create a new vertex, a big guy, and make it reach, because a directed graph, you connect it to everybody and put 0, 0, 0, 0 on these things, and then now everybody is reachable from this new source vertex. Run Bellman-Ford from this new source vertex. Then you will detect whether there is a negative length cycle in the graph. Okay? That's all I'm saying. Yeah? Okay? So in nm time you can do that. Okay. Okay. What about shortest path tree? If you don't detect a negative length cycle, the algorithm will automatically give you a shortest path tree also. How? Either the algorithm will detect a negative length cycle, then there is no shortest path tree, right? That doesn't make sense because I can go around. Otherwise, I know shortest paths are well defined, right? If there is no negative length cycle. So you'll also get a tree. How will you get a tree? Whenever you have shortest paths, the distances should tell you how you got the distance, no? So you always keep a pointer to the guy who gave you the distance. Okay? Remember, if there is no negative length cycle, dvn-1 is your shortest path distance, right? Yeah? So how did I get to dvn-1? Right? I remember how I got dvn-1, right? How do I get dvn-1? It's either dvn-2, in which case I already know the shortest path distance, right? Or I updated my distance in dvn-1, right? So that means that somebody gave me the distance, right? Some dun-1, n-2 plus that. So I keep track. Who gave me the current distance? I always keep a back pointer. Those back pointers will give me the shortest path. Yeah? The same as Dijkstra's algorithm. It's just that whenever you compute distances, you are also computing how you got those distances. Okay? So that will give you the shortest path. Okay. Very good. So now I want to say something which is very important for DAGs, because DAGs are special. We know DAGs are special. They are part of the structural characterization of directed graphs. What is the nice thing about a DAG? No cycles, right? So there cannot be negative length cycles, right? You don't have to worry, right? DAGs are nice because there are no cycles. So there's no reason to worry about negative length cycles, right? Because there are no cycles. So shortest paths are always well defined, right? Even if there are negative length edges, right? This is one class of graphs where you are guaranteed there are no negative length cycles. Okay, but there's more to it. Whenever you think of DAGs, what is the first thing that you should think of? Okay, two things maybe, okay. Sources and sinks, right? They always have a source and a sink. What's the consequence of that? It's always a topological sort, right? Okay, the exam is coming up. Even if you don't care about this, you have to think about it, right? If you see a DAG, topological sort should come to your mind, and sources and sinks, because that's a nice structural property of DAGs, right? Okay, they're related. Okay, the question is, can we find shortest paths in DAGs any faster than we can in a general graph? Okay, and it turns out, first remember, you don't care about negative lengths or positive lengths because there are no negative length cycles, everything is well defined, right? Okay, it turns out because of the topological sort, the shortest paths are also very easy to compute. Okay, the reachability is very simple. Okay, so I'm just solving the shortest path problem in a DAG now. It becomes very simple because, why does it become very simple? So let's look at the topological sort of the DAG. Okay, where is the source? If the source can be somewhere, right, in the middle of the topological sort, what about all the guys who come before him in the topological sort? So they're not all sources, but can S reach any of them? If S is in the middle of this topological sort, what about all the guys who came before him? They cannot be reached by S, right? Because all the edges are only going to the right, right? So everybody who's to the left can be thrown out of the graph, right? Yeah? Because you can't reach them, right? S cannot reach them, right? So you might as well assume without loss of generality that in a DAG, the source is the first guy, the topological sort, because anybody who is before the source can be thrown out because they cannot be reached by S. Okay? Okay, so we can assume without loss of generality that the topological sort is V1 to Vn and S is the first guy, V1. Okay? Now I want to find the shortest path from S to everybody. How can I find that? Well, what do we know about any vertex in the middle of the topological sort? How can he get his shortest paths? Can the shortest paths for V1 to Vi depend on Vi plus 1 to the other guys? No, right? Because their paths can only go to left to right, right? So I can compute the shortest paths in increasing order of this topological sort. Right? In fact, I cannot reach, Vi cannot be reached by anything Vi plus 1 to Vn, right? Forget the length. I cannot even reach Vi from the guys who are after me. Okay? So that simplifies the algorithm substantially, right? Shortest path from S to Vi cannot use any node from Vi plus 1 to Vn, right? Okay? So I can find the shortest paths in increasing order of this topological sort. Okay? So the algorithm is very simple. So here is the algorithm, right? I initialize everybody's distance to infinity. The source is the first guy, remember, because we threw out everybody before. So dss is 0. Then for I equal to n to n minus 1. So I already found the distance from V1, which is a source, to the first I guys, right? So I want to find the distance to the I plus 1 guy. How do I find it? How do paths to Vi plus 1 look like? How do I enter Vi plus 1? Through some edge coming from the before me, right? So what is its shortest path? So this is Vi plus 1. The only edges coming into it are like this, right? I already know the distance from S, the source, to all these guys, right? And I cannot go, nobody from here has a path to Vi plus 1. So the shortest path to Vi plus 1 is the min over all these edges coming in, the distance to this guy plus this, or this guy to this guy to this, right? Take the min of, for every edge coming into Vi plus 1, look at the previous guy, look at his shortest path distance. I already computed it, right? take that plus the length, that will give me the shortest path to this guy using that edge. Take the min of all this, that will give me the shortest path distance from the source to Vi plus 1. Yeah? Okay? So, for each edge Vi, Vj in, let's see, Svj, okay, I'm doing it in the forward order. So, this is doing it in the following algorithm is a little different from what I said. What this is doing is that once I find the shortest path to Vi, I'm updating all the shortest paths to the guys who come after him. Okay. I'm sorry, this algorithmic description is different from what I gave here, but the idea is that when I'm looking at the ith guy, I only need to look at the guys who came before me, right? One edge before me, all the edges coming into me, and I already computed the shortest path to them, so I add that edge length and take the minimum over all those edges, and that will give the shortest path to the current guy. Okay? Yeah, so you start with the leftmost guy who is the source in the topological sort, walk one by one, and at each step, the amount of work I need to do to find the shortest path distance is precisely the in degree of the guy, right? So the total work I do is only linear. Okay? It's a very efficient algorithm because the DAG is such a simple structure. If I do the topological sort, the shortest path computation can be done in linear time, O of n plus m time, right? Whether the edges have negative lengths or non-negative lengths. It's right. It is not like it's even better than Dijkstra's algorithm. That's what I'm trying to say, right? And it will work for negative lengths also, right? So it's a very simple algorithm, right? And so that's good, right? DAGs are easy because Dijkstra's takes m log n or m plus. No, that's linear time, right? Topological sort takes linear time to create. Everything is linear here, so it's very efficient. You don't have to do work, so much work. Okay, yeah, it's faster than Dijkstra's algorithm. That's what I'm trying to make, and it can handle negative length edges. That means you can actually find longest paths instead of shortest paths. Okay, this is important for your homework. Okay, how do you find longest paths? By negating, right? If I want to find the longest path, I can do a negation, and that's finding shortest paths with the negative lengths is the same as finding longest paths with non-negative lengths, right? Okay, but then if I have negative length cycles, I'm in trouble, right? Because if I negate things, I can create cycles. But in a DAG, I cannot create cycles, right? So you can play all these games. You can take edge lengths which are positive and negate them, and I'm happy because I'm not going to create any cycles for you. And now I can find shortest paths even with negative lengths, right? Because there are no negative length cycles. So you can find longest paths in DAGs, and so that's actually useful. Okay, so I want to say something else why DAGs are important, right? Not just because we can solve shortest paths on them. Let me tell you how to do Bellman-Ford just using DAGs. Okay, all right. So this idea of layering, which I hinted at so here is a trick, right? I want to find shortest paths in negative lengths in a graph, and I want to compute these dvk values, right? We came up with a recursion for that, right? Okay, but here is another way of doing it without any recursion, very simply using graph theory, right? Create many copies of the graph. So this is V1, V2, okay, is this graph make sense? So I have a graph, original graph G, and I create a k-layered graph out of that. Okay, how did I do that? I took the vertices and made one copy, two copies, three copies, k copies. Okay, now there are no edges within the copy, but what are these edges between two layers? Remember, if this is a copy of U here and a copy of V here, what is the length of the edge I put there? the length of the original edge between u and v. Okay? Is it okay what I did? I took the original graph G and I created this layered graph out of that with k layers. Okay, any k you want, right? So I can take a source vertex and connect it to all the vertices that it is connected to in the original graph. What does this graph look like? Yeah, so what is this a DAG or no? It's a DAG, no? Yeah? Agreed? All right. So what is the shortest path distance from S to a copy of a vertex here? What is the meaning of that? If I did this. How can I get from S to this vertex in this copy? How many edges can I use? K, right? So I claim that once I take this graph and create this graph, if I compute a short, remember it's a DAG, right? I don't care, it has no cycle. So I can, whether the edge lengths are negative or positive, I can create shortest paths, right? In linear time. Yeah? Linear in this graph size, right? How many edges does this graph have? If the original graph had m edges, this has mk edges and nk vertices, right? Okay. No, but what is the meaning of the length of the path from S to this vertex in this graph as opposed comparing it to this graph? I claim that you will get the shortest walk length from S to this vertex in this graph with at most k edges. Is that okay? Okay. See, I'm using only k edges of the original graph, no? But I can use the same vertex many times because I have created copies here. Okay? But I'm getting the shortest walk length from S to U with at most k vertices, k edges by computing shortest paths in this DAG. Okay? So what I'm trying to say is that you can reduce the problem of limiting the number of hops by just not thinking about recursion, but by doing this graph construction. Okay? So this is another tool you should think about. Graphs are very powerful, right? So we didn't worry about recursion here. We just took the original graph and created this layered graph, which prohibited you from using more than k edges because it has of the structure. But you are allowed to use a vertex many times, so you are getting walks instead of paths, right? Okay? So now computing shortest paths in this DAG is similar to computing shortest walks in the original graph. Okay? That's what I'm trying to say, that the running time you get here is a little less efficient than Bellman-Ford, but these graph constructions are very powerful and important. And DAGs are important precisely because they enable you to do this layered construction, which gives you structure on the things that you're looking for. Okay? This is a graph reduction, which is very important, right? Right? So DAGs are important for that too. Okay. All right. So we have very little time. Well, we have 15 minutes. So I'll tell you a little bit. This is just an extension of the shortest path problem, right? So far we have been only working with what? One source, find the shortest paths to everybody. Suppose I want to find all pair shortest paths. What does all pair shortest path mean? For every pair, I want to find the shortest distance. Right? How will you do it? Well, you know, one obvious thing is take every source, compute shortest path distances, and right? Is it good or bad? Well, the answer is that we don't have any better algorithm than that. Okay. No DAGs, general graph. We are done with DAGs. Okay. Okay. So that is what's called the APSP problem. Right? It's a very simple, important problem. Right? For every pair, I want to know what is the shortest path distance. Okay. Well, we saw single source. That is okay. So let's break it down. If the edge lengths are non-negative, Dijkstra's algorithm is good, right? M plus n log n. Bellman-Ford is what? Mn, right? Okay, that's much. See, with negative lengths, our running time is much slower than with non-negative lengths, right? Mn is pretty bad, right? If you have a big graph, Mn is pretty bad, right? But that's the price we have to pay because negative length edges are there, right? Dijkstra's algorithm is almost linear, right? Okay, so if you want to do all pair shortest paths, you can just run this algorithm n times from every vertex, right? So then Dijkstra's algorithm will be what? It will be Mn plus n square log n, yeah? n times Dijkstra's algorithm, right? What about Bellman-Ford? Oh, that's already slow. If you do n, you'll get n square m, right? Okay, that seems pretty slow. And it could be n to the 4, right? So it turns out that there are two things you can do. You don't have to spend n square m, you can do nm. Even to find all pair shortest path with negative lengths, as long as there is no negative length cycle, you could do it in nm, right? There's one trick involved to do that, but I'm not going to do that. So here is another, it's a very clever trick, beautiful recursion. I want to expose you to it because it is such a funky recursion, right? This is called the Floyd-Warshall algorithm, right? It's another dynamic programming. It's very, very funky. I don't know how they came up with it, right? But I just want to expose you to it, right? Because it has a nice application. So here is the whole point of Floyd-Warshall algorithm is to understand what they're trying to do, right? Look at this graph. I've numbered the vertices 1 to n, okay? Without loss of generality, 1 to n. I'm interested in this quantity called Dijk. Okay, the whole thing is, what is Dijk? It is the shortest path distance from I to j, except that I'm only looking at paths where k is the largest index on the intermediate vertices. Okay. Yeah, see, this is the definition is tricky. Okay. Okay. Okay, vertices are numbered 1 to n. Okay, every vertex is indexed, right? It is important to index it. Okay, vertices are numbered 1 to n. So what is Dijk? Dijk is I look at all paths from I to j. Okay, I and j have to be on this path, right? There's no choice. Okay, all right. But what about in the middle? Okay, okay. Dijk means that I'm only allowing you to vertices 1 to k in the middle. Okay, according to my numbering, we fixed the numbering, right? Okay, so example is better. What is Dij0? Remember, these are the indices of the vertices. What is Dij0? Meaning, Dij0 means I cannot use anybody in the middle. Okay, is that okay? What is Dij0? 100? Yeah, because I'm allowed to use only the direct edge, right? If there is no direct edge between I and j, it will be infinity because I can't use anybody, right? What is Dij1? Dij1, I'm allowed to use 1 along the way, right? I mean, 1 to 1. So Dij1 is what? 9, right? Okay, yeah. What is Dij2? Yeah, at most that number. Yeah, I mean, that means that vertices 1, 2, right? K. What is Dij3? 5, right? I can use anybody, right? Is it clear? Yeah, is the definition clear? Okay. Now, okay, why did they define this, right? Okay, so okay, you can do this exercise later. So you can write a very simple recurrence for Dijk. What is Dijk? Dijk is either Dijk minus 1, yeah, right? What is Dijk? Remember, I'm allowed to use 1 to k in that path, right? But maybe I don't need k, so it's enough to use 1 to k minus 1, right? Or if I need to use k, then it is Dik k minus 1 plus Dkj k minus 1. Okay, what does that mean? Either my path doesn't have k in it, in which case I will just say Dij k minus 1. But if I have k on it, what does that mean? I go from I to k somewhere and then go from k to j, right? But on the path from I to k, I don't need to use k at all, right? Remember, it's a path, shortest path, right? So it is Dik k minus 1 plus Dkj k minus 1. Okay? Very simple but funky recurrence, right? Okay, what is my shortest path distance from I to j? This Dijn, right? Because I'm allowed to use everybody. Okay, okay. This recurrence is based on 3 things, not 2 things, because all 3 parameters are changing, right? Okay, this is a little tricky. Okay. So how many sub-problems do I have? I have n cube sub-problems. Okay. And what changed, the index of these changes, don't worry about the thing. You can use this recurrence to compute shortest path distances in n cube time, all pair shortest path distance in n cube time. Okay. Because remember that work to do compute dijk is only 2 times, right? Constant, if I have all these values, I'm only spending constant time to evaluate dijk. The n cube guys, I spend constant time to evaluate all of them, so I'll get dijn for everybody in n cube time. Okay, that's the Floyd-Warshall algorithm. Okay, it's a very funky algorithm. It finds all pair shortest paths in n cube time, right? It is not so useful in itself because it takes a lot of space. But the recurrence is very, very important, right? It's a very funky recurrence. So why do I say that? It's very interesting because don't worry about this. It's because we left one piece when we did finite automata. Okay, what did we not do when we did finite automata? We showed that NFAs are no more powerful than DFAs, right? We showed that NFAs are at least as powerful as regular expressions, right? That was easy too, right? One thing we didn't do was that regular expressions are as powerful as DFAs and NFAs. Maybe you forgot all of it, right? See, we went one direction, right? We defined regular languages, then we defined DFAs, then we defined NFAs. NFAs are clearly more powerful than DFAs, at least from the definition itself. But we will prove that, no, they're not more powerful than DFAs because for every NFA, we can convert it into a DFA. Okay? And we showed that regular expressions can be captured by NFAs, right? From every regular expression, we can create an NFA. What does it tell us? It tells us that, regular expressions are not stronger than NFAs, right? NFAs are the most general one. What I wanted to tell, we claimed that for every NFA, we can create a regular expression. So regular expressions are as powerful as NFAs. Okay, we didn't do the proof. Why? Because it's difficult. Okay, but the reason why it's difficult is because we needed this recursion. This Floyd-Warshall recursion is what gives us the thing. Okay, because what do we want to do? I want to convert a DFA into a regular expression. Yeah. If I give you a DFA, can I create a regular expression? Yes, that's what we want to do, right? But DFAs are graphs, right? You should think of DFAs as graphs. So somehow something of the graph is important, and we didn't do graph algorithms and this recursion there, so we couldn't do it so simply. But now that we've seen graphs for a while, I'll sketch how to convert a DFA into a regular expression such that the regular expression is equivalent to the DFA. Okay? All right? So it is a little tricky, but if you run out of time, you can look at it later. So what is a DFA? It's a machine. It has n states, right? I'm going to number them 1 to n. And now the whole, and I want to prove that there is a regular expression that captures language accepted by this DFA. Yeah? That's what I'm trying to prove to you. Okay. Yeah, is that clear? I give a DFA. So, okay, here is a DFA. Okay. No, not graphs are DFAs. DFAs can be understood via graphs because there is a graph sitting there, right? Right? And I'm claiming that given a DFA like this, I can show you a regular expression such that the language accepted by this DFA is exactly the language accepted by the regular expression. Yeah? We didn't do that proof, right, previously, right? Okay, so how do I do that? I start with a DFA, any DFA. It has some number of states, right, finite number of states. Let's call them Q1 to Qn by arbitrarily numbering them. Let's define this language called Lij. For every I and j between 1 and n, I can be equal to j. Lij is what? The set of all strings that take you from state I in the DFA to state j in the DFA. Is that a regular language? Yes, because that's a DFA, right? I can make I the start state and j the final state. Yeah? Is that regular language? Yeah? Okay, Lij is a regular language for every I and j, right? Okay, what is the language accepted by the DFA? It is the union over all the final states of L start state I, right? Okay, without loss of generality, let's make the start state to be the Q1. Right? Q1 is the start state. What is the language accepted by the DFA? The set of all strings which take you from what? The start state to some final state, right? Yeah? Okay, so but that's all I wrote, right? The language accepted by the machine is the union over all the final states L1I. Right? What is the definition of L1I? The set of all strings which take the machine from the start state 1 to that particular state I, right? By taking all of those strings, you will get precisely the language accepted by the machine. Yeah? Agreed? Okay. Okay. So now this is the funky recurrence which is precisely defined by the Floyd-Warshall thing. Now let me define Lijk like we did in the thing. What is Lijk? This is a set of all strings that take you from state I to state j, but along the way you don't use any state other than 1 to k. See, we're talking about graphs now, right? We're thinking about DFAs, but we're talking about graphs. What is Lijk? It is a set of all strings that take you from state I to state j, but along the way in the intermediate states you cannot use anything other than 1 to k, just like in the shortest path, right? So Lij is precisely Lijn, right? Just like in the shortest path case. You're allowed to use anything, okay? Okay, but you can write a very simple recursion for Lijk. Lijk is Lijk minus 1, that you don't use the kth state, right? So it's a set of all strings which take you from I to j using only 1 to k minus 1 in the intermediate thing. Or you can also go from I to k using k minus 1, okay? And any number of copies of going from k to k using k minus 1, followed by going from k to j using only k minus 1. Okay, so you have to think for a little bit that this is the Lij can be written as this language. Okay, this is the recursion that we saw in Floyd-Warshall. Okay, but if we inductively, if each of these is a regular expression, you can see that this is also a regular expression, right? Because we only use unions and Kleene stars. Okay, if Lij k minus 1 had a regular expression, you can create a regular expression for Lijk using this formula. Okay, and then you will get Lijn as a regular expression, and then you take all these unions, you'll get the regular expression. Okay, okay. Now the point is that all I'm trying to make is that the way to convert a DFA into a regular expression is precisely using the same idea that is in the Floyd-Warshall recursion. Okay, that's the high-level thing. You know, it's a very complicated, messy algorithm. In terms of practice, it will create a huge regular expression, but it formally proves to you that if you have a DFA, you can write a regular expression using this algorithm. But see, we couldn't do this so easily without knowing graphs and the shortest path intuition, right? It is complicated, but that's the idea of the Floyd-Warshall. Okay? So this finishes the formal proof that you can convert a DFA into a regular expression. We don't need this for the exam or something, but if you're interested, you can use it.
I don't quite remember. Why is Lij regular?
Oh, because you can create a new DFA where I is the start state and j is the final state, no?
It's every DFA regular.
No, that's another DFA, right? You know, yeah, sure.
So every DFA can be represented as a...
No,